So here we're going to be doing ODE int solving on Python. Start by making this huge. Look at that! Whoa, huge! No, it's tiny. Come on, Zach, can you read that? So first I'm going to look up ODE int Python solver example. I'm using DuckDuckGo, so that's kind of nice. I'm going to go to AP Monitor because I really like the way that this is set up. It actually follows the... Why is this so zoomed in? I thought I zoomed out. There we go. So I really like all of that code that's right there. Legend. Let's zoom back in. Yeah. Okay, I think that's good enough. This is readable from a distance. So basically what this is going to do is, here is the ODE int function, and this is brought in directly by the SciPy module in Python. Here the model is, this is the function. It's given as a function of time. So here, if you don't have time, you need to have a unique variable that you could consider to be time, something like that. Initial conditions, this is going to be your y0, t, time. You're going to need an array of time values. Calculate. Here, and it goes into an example, provides this. I'm going to completely ignore this and go down to exercise 3, completely ignore this, and pop up the code, which I'm then going to copy. Okay? So the whole reason why I like this code is, what you'll notice is this defines two different solutions, and then it combines them into one. Okay? I'm going to go ahead and take this framework and I'm going to adjust it to a brand new solution. So, pop open my programming. You'll notice I've already done this, but I'm going to pretend like I haven't and go ahead and pop open. This is the code that I directly obtained from that website. It's at apmonitor.com / well, here, I'll just zoom in on that. I just looked up ODE int, all one word. Yeah, that's it. If you scroll down to keep going, keep going, keep going, keep going, keep going. Problem 3. That solution, what it does is it shows you how to do multiple multiple derivatives all at once.
You did problem 3.
Yeah, I just copied problem 3. Now the nice thing about this website is there are a lot of different, very unique things that this shows. So here, if I go up here, this shows how do I plot it with 3 different constants. So if you were looking from a design aspect, say one of your constants at the very beginning of your equation, you wanted to see how changing that one constant is going to change your solution. This is what it did. It just input 3 different k values in to the exact same model and then plotted how the solution changed as a result. All right, so that's kind of fun. This is an excellent resource. I actually really love the way that this explains it. And then I screwed everything up when I made my last video, but you can ignore that part and focus on the fact that I'm the smartest person you know. Oh, the pretty little lies we tell people. All right, so here is the code that we have. Now what I'm going to do is, first of all, if you copy code from anywhere, usually it's a really good idea to copy the website that you got the code from. Why? Because it's really easy to screw this up and then not go back to the original, lose the original code, and not know what to do. So, this is why pseudocode is so valuable. Okay? Alright, so this is just the exact code. If I go ahead and run this, if all of my libraries are working properly, this code will execute error-free. You'll notice I get this funky little window up here, and that is a pretty looking graph. If we were to zoom in on that, it's a blue line with a red dashed line on top of it, because that's what the example problem does. Okay? Alright, so now how can we take this and do something out of our own? Now, when I was in class, we provided the just generic ODE solution of f is equal to dx squared dt squared plus 2 alpha dx dt plus omega naught squared x. Okay, that's our generic solution. So what I'm going to do in my pseudocode is I'm going to go ahead and add a little bit of space, and then go ahead and write out explicitly, here's what I want to have happen, okay? This code solves the complex ODE system associated with the second order derivative function f of t is equal to dx squared dt squared plus 2 times alpha times dx dt plus omega naught squared times x. Okay, we're here. F of t, forcing function. X is the independent variable. Nope, dependent variable. My bad. The forcing function is technically the independent variable. Alpha and omega are the coefficients from the constitutive equation. Okay? Alright, so just pseudocode giving some background as to how I'm about to modify this code. And also this is how I don't have to turn my computer around and go draw this on the board, which would have been a lot easier. But I don't want to do that. Okay. So, this is our ultimate goal. I guess I should add in here. The system is broken. Following way. I'm going to go ahead and call it V1 dot is equal to f minus 2 times alpha times v1 minus omega squared times v2. Okay, so I'm just going to change my variables here so that x is equal to v2, x dot is equal to v1, and x double dot is equal to v1 dot. Okay, now since I have two variables here, I also have to identify v2 dot is equal to v1. All right, any questions so far? All I've done is we've done this in class so far. This is just how you break a function into multiple single order equations. So now we have this. We're going to leave this piece intact for now and go down here and start looking at how everything down here looks. So here we've got our initial conditions. This is given as a vector. Okay? The vector, the importance of this vector is that this first one has to be written in order of what variable is addressed first. So I'm going to add in a little bit of pseudocode because you know me, can't resist it. This is going to be z is equal to bracket v1 comma v2. Okay? So that's how I'm going to orient this. Now when I go up here, I'm going to change this around. So this is going to be, they have it dx dt. I'm changing it to v1 dot. And then v2 dot. Okay, so here my equation for v1 dot, let's scroll up to right here, is f minus 2 times alpha times v1 minus omega. And here, note this, we can't use the caret. We have to use the 2 stars anytime you do a square. Otherwise you get a weird error. And then we multiply that by v2. Okay, and then down here, we have v1. So if I need to add a little bit of pseudocode, there, v1 is equal to x dx dt, and v2 is equal to d v1 dt. Okay? All right, now I can leave this as is. I'm going to have to change this to v1 dot v2 dot. There we go. All right, now I do have an issue. F is itself a constant or a variable. I don't actually know. It's a function. It's a thing. It's a thing. Okay. Here there is no explicit dependency on t, because the way that we have our equation set up, we never had a t. The only explicit relationship we could have is if we were to take f and actually make it a function of time. So what I'm going to do is I'm going to go ahead and define my coefficients in here. Actually, no, I'm going to follow the lead of this one right here and go ahead and write in the actual args statement. Args, like pirates. So that's how I'm going to address it. It's actually called in the ODE int function. Okay, and what that'll allow me to do is allow me to change my arguments. If I wanted to plot this multiple times, it wouldn't be defined by the function up here itself. All right, so the way that I do that is I go in here and I'm like, comma, args, and then I put in f, comma, oh, I guess it requires bringing in k, so we would have to make f, comma, alpha, comma, omega, and we'll have to put that up in the model. So here, if I go back to my model, comma, f, comma, alpha, comma, omega. Okay, so I'm bringing in 3 additional variables into this function. So now down here, I've got my args, f, comma, alpha, comma, omega, comma, and then you just have to leave it as a comma. Okay? Put a space in there for good measure. And then end that with a parenthesis. All right. So one other piece now is we actually have to define what f is. So here, define your coefficients in your forcing function. F is going to be equal to np dot sine of t. So this is going to be a sinusoidal function. Here we brought in numpy as np. np dot sine is the function, a sine function. And then we'll have alpha. It's going to be equal to yes, we'll make it like 5.1. And we'll make omega equal to like 1.1. Why not? Okay, now we should probably go down here and look at all this plot stuff. You got your y label here. We can go ahead and leave that as response. Legend is best. Might as well change that one. When I run it, oh, it's going to tell me it doesn't like args. Comma t, comma args equals, oh, it's args equals. There we go. Oh, yeah. Probably should do that, huh? Here's z. Okay. When I bring in v1, v2, v1 represents this first equation, represents this right here. v2 represents, so every time we have a v1, it represents this first equation. Okay, that's the way that our initial conditions are written out. Every time we have a v2, that represents this, which means that v1 is equal to z bracket 0, which is the first entry, and v2 is equal to z bracket 1, which is the second entry. All right, so when we go up here into this equation, we have to replace our v1s with z bracket 0, and our v2 with z bracket 1. Okay? Now when we run it, should work. No, of course it's not going to work. Why would you work? Why would you not make this more difficult for me? Setting an array element with a sequence. Darn you. Darn you. An array element with a sequence would mean, I think I have to set this up like this. And then just call this F. All right, hold up. Don't follow what I'm doing yet. I'm going to see if this works. F1, F2, and this would be F0. Not sure if that's going to work. Oh, look, it did. Not work. Nice. All right, well, I'm just going to scrap this idea. We'll go ahead and plug it into the model. I don't want to figure that out on the video. But that is something that eventually I would like to do. So I'm going to go back into my model. and set my f value here. All of these things. I'm just going to go ahead and cut this and paste it into my model itself. I'll have to grab these and tab them over. But now we have them included into the model itself. There we go. So if I run it, now this should work. Right? Nope.
It's because you solved the...
Right. Because I forgot to unscrew them up. Okay, so now that they're unscrewed up, now this should work? Hey! Still give me an error message, but whatever. And the labels on this is not right. Doesn't tell me Kale's the best though, so I'm kind of sad about that. But this now becomes our response between 0 and 5 seconds, assuming initial conditions of 0, 0. Okay? So you'll notice that here, the second one is actually the x position. The first one is the x velocity, or the x dot position. Okay? So keep that in mind. It's kind of interesting. But the way that we set this up was number 2 is going to be your V2, where your V2 is set at, no, V1 is dx dt. Oops, I did that entirely backwards. Didn't I? No. I did. I totally did. Nice work, me. This is actually V2 dot. And this is V1 dot.
Yeah, so you could
well, good job, me. Never a dull moment. Have to change that one.
Is it supposed to look like this one?
With a constant line? I don't think you're supposed to have a constant line. Let me see what mine gives. Yeah, no, all it's going to do is it's going to switch them, which is what you would kind of expect.
Do you mind scrolling up again?
Yeah, I can.
Thank you.
Bruh. Okay, here's how we're going to change our formula functions. This is kind of interesting. That's how you establish a fraction. So here, I'm going to go ahead and change. My first label is dx dt squared. So I'm going to go ahead and put this as dx squared dt squared. Oh. Like that. And that's going to be equal to f that is a interesting. That's how you make it go on multiple lines. So I don't want to do that. F minus alpha then bracket dx dt minus omega exponent. Oh, I'm just playing around with titles now.
And so what's your graph supposed to look like here?
Alright, so if I run this again, let's see if I screwed up the formatting. Oh, no, it totally worked. So here the blue line is the second order differential solution. And this one is just the single order solution. That's funny. Okay. So that is the basic solution method. Now, I am going to screw around just one more time because it's going to bother me if I don't. I'm going to screw around with how to change these variables and leave the forcing function the same. So we'll go ahead and try that. We'll see if there isn't some assistance that can be provided from up here. Oh, args is just a tuple sequence. So yeah, a couple of other examples. I really screwed up args. That's too bad. Well, if I feel like that's necessary, we'll do it again. All right, I'm going to go ahead and end the live stream at this point. And